Okay, everybody. This is the practice problem review session for our exam 3 for MCT 2270. Couple of notes as usual. Watch this video at 1080p HD resolution to be able to read the questions on the board, or in this case you've been provided the handout that has the same questions given to you. The other note is that I've already done a lot of the calculator portion in advance, so feel free to pause this if you need. We're just going to be going through the equation side of things. All right, and these are only the mathematical type questions for the exam, not the conceptual. All right. First question. A system of molecules has 1 trillion possible configurations. Using the Boltzmann equation, calculate the entropy of this system. All right, so we're going to write up the Boltzmann equation, which is the entropy equals the log of the number of possible configurations, which is omega. Because we're dealing with a physical system, and this equation is being used in the sense of physics, we do have this Boltzmann constant, Kb, right here. And just to remind you, the value of Kb is about 1.38 times 10 to the minus 23. Okay, it's a very small number. So this is the equation to use in this case. Plugging in numbers, we have 1.38 times 10 to the minus 23 ln of 1 trillion. So 1 trillion is actually an impossibly tiny number of configurations for any real-world system. They're usually absolutely massive, the numbers of configurations. But in this case, so that we can do calculations, we're using a trillion, which is 10 to the 12th, okay? So really, it's just a matter of punching this into your calculator properly. And when I do this, I get out an answer of about 3.183 times 10 to the minus 22nd. And the units on that are joules per Kelvin, because it's an entropy. Okay, next question. 2 nickels are randomly flipped, each appearing heads or tails, so it's a binary choice. Using the Boltzmann equation, calculate the entropy of this system. So I'm going to again write the Boltzmann equation, S equals ln omega. This time, when we evaluate whether or not to add that constant, we realize that this isn't talking about molecules or any physical system. So this is using the information or statistical approach to entropy, which we've discussed means that we leave out that constant that gives units. So our answer here will actually be without units. All right? Now, where to begin on this? Well, we need to figure out how many possible configurations a 2-coin system has. So the way that we might do that is look at the probabilities. Remember that we had omega equals 1 over the probability for our simple case here. So I can rewrite this equation as S equals ln of 1 over the probability. So if I can find the probability of any given coin flip with these 2 coins, I will use that to calculate entropy. So let's look at the probability of coin 1 and the probability of coin 2. We'll make a chart. It's actually not that detailed of a chart. For any given coin flip, heads or tails, there's a 50-50 probability for coin 1. So the probability for coin 1 is 1/2. This is P probability going across. For coin 2, it's the same. It's 1/2. Those are independent probabilities. So the way we add independent probabilities for the 2-coin system, coins 1 and 2 together, is we multiply them. So independent probabilities add like this. 1/2 and 1/2 is 1/4. That means that for any given configuration like tails heads or heads tails or heads heads or tails tails, there's a 1/4 chance. And that's obvious because I just listed out the 4 possible options. So if you did go, okay, 4 possible options, that's omega. You could just put 4 and use this. Or you could think about it in terms of probabilities and realize that this is ln of 1 over 1/4, and this is a complex fraction, and so the 4 flips back up to the top. And we have, of course, 4, which is our number of possible configurations. So this numerically comes out to about 1.386. And again, no unit, because this is using the version of entropy without the units of joules per Kelvin. This question here, which has a higher entropy? A 4-digit code using numbers 0 through 9, I miswrote this question, numbers 0 through 9, or a 3-digit code using letters A through Z. So we don't even have to calculate the entropies. I'll throw them up, but all we need to know is which one has more possible configurations, because the log is a monotonically increasing function, which means that if we find the higher value of omega for number of possible configurations, we have found the higher entropy. All right, so we are using this equation, but we're really just looking for what is omega in each case, the number of possible configurations. Well, let's look at the 4-digit code using numbers 0 through 9. There are 10 numbers, okay? Omega for the numbers. There are 10 of them, and so that means that we have a chance for the first number of 10. Then these are independent probabilities that are being added, so we multiply. For the second number, we have 10, as well as for the third. So each one of those, there's 10 possible digits, 0 through 9. We can multiply them all up, and we get 10,000 for omega using a 4-digit code with numbers. Now, omega with letters, well, the letters A through Z, there are 26 of them. And in this case, we have 3 of those, 3 different letters being used in our 3-letter code, and each one is independent. So again, multiplying independent probabilities, we have 26 times 26 times 26, which you can do on your calculator in one step, doing 26 to the third. And that comes out to be 17,576. So the question is answered already. It's the 3-digit letters that has the higher entropy, okay? Or higher disorder, some people may say randomness. And so if you're trying to create a more secure code between these two options, you would go with a 3-digit code using letters over a 4-digit code using numbers. If you want to compute the entropies, you simply take the log of each one of those numbers. So the entropies for the 4-digit number code, I did the log and I got 9.21. And entropy for the letters, I did the log and I got 9.77. So you can obviously see that for the letters, there's a higher entropy. Okay, moving on. A cup of coffee starts at 370 degrees Kelvin. It loses 10 joules of heat to a room at 310 Kelvin. What is the reversible entropy increase of the room during this process? Well, we're going to look at this and realize that this is one of those scenarios where we're dealing with a large thermal reservoir, the entire room. Just that little amount, that 10 joules of energy being dumped into the room, does not change the overall temperature of the room. We approximate it as staying constant at 310. So we can use our isothermal formula for the reversible entropy, which is the formula that we learned first, that delta S is minus delta Q over T. Hopefully that rings a bell. Now there's only one temperature in the equation, and we're given 2 temperatures. The starting temperature of the coffee and the temperature of the room. Well, we're asked about the reversible entropy increase of the room. So in this problem, the T in the bottom is going to be 310 degrees. The 370 degrees is given to you to confuse you. It's not used in the problem. Delta Q is a heat loss. It loses 10 joules. So we have this, the minus sign from the equation, and of course the heat loss of 10. And this comes out to simply be, the minus signs cancel, 10 over 310 is 0.0323. Joules per Kelvin. Simple enough, it's just a division problem, really. Okay, the next one builds on that. During the process above, the previous process, the total entropy increase of the room is measured to be 12 joules per Kelvin. Now, a special machine gathers all the energy from the room and puts 10 joules of it back into the coffee, reversing the process. That's the key. There are many ways to do this, but we know that it's the exact reverse of the process we just did over here. What is the total measured entropy decrease in the room? So when we take that process of coffee losing heat to the room and we reverse it, what is the entropy decrease we're going to measure? We measured 12 degrees going one way. Now, you may be tempted to do something simple, which I want to warn you not to do, and look at this and say that the entropy increase of the room going one way was measured to be 12. So the entropy decrease of the room going the other way must be negative 12. That is not correct, okay? Here's how we actually go about solving this. For the one-way direction, let's call it the forward direction. Everything in this equation will be for the forward direction, and that happened in this process, okay? We have the delta S total equals the delta S reversible plus some bit of entropy that's generated. Remember that this is like the perfect portion, and this is the imperfect part that we cannot get back. This total amount we have from this that was measured to be 12, okay? The reversible portion is what we calculated, 0.0323, and S gen is our unknown. If I subtract this over, I get an entropy generated of 11.9677 joules per Kelvin. All right, so it actually turns out that most of that measured entropy increase was just generated entropy. This is entropy we can't get back. So when we reverse the process, we don't get it back. Let's do the reverse. Now, that special machine is going to reverse it. This time, write down the same thing to start. The total entropy decrease was, this is the unknown. Yeah. Yes, the total is what's unknown, okay? So we know the reversible is just the minus of this, because the reversible portions, the perfect parts, always cancel each other perfectly. So if this much was generated going forward, then we're gonna get that all back going backwards. So negative 0.323, but plus the entropy generated, which is the same forward and back if it's the same process. So if this much was generated forward, well, that much is generated backward as well. Okay? And we get out a final answer for S total of 11.9354 joules per Kelvin. Circle my answers here. All right. So that is how we solve these type of problems. Moving on A steady state airflow duct narrows, increasing the flow rate from 1 kilogram per second to 1.3 kilograms per second. So we've got like a nozzle here. As it comes in, it's wider and it's flowing slower. And as it goes out, it's narrowed a little bit, but it's making it flowing faster, okay? How much entropy is generated each second by turbulence and other irreversibilities? That's the imperfect portions, the actual generated entropy. Use a specific entropy for the air of 5,000 joules per kilogram Kelvin. Well, let's write this formula down again over here, okay? Change of entropy total equals delta S reversible part plus entropy generated. But this time we're talking about per second. It says how much entropy is generated each second, and we're given the mass flow rate in kilograms per second. Those are two separate hints that what we're talking about here is the dotted version of this equation. Okay, so it's entropy change per unit time. Now, it says right here steady state. So hopefully you remember that that means this side is 0. So to write what we have so far, 0 is delta S reversible plus S gen dotted. And then I can simply move this over and say that minus delta S reversible equals S dot gen. This is the thing we're going for. So we're going to have to compute this side. All right. So what we're going to do is realize that we're given mass flow rate and specific entropy. And we want delta S dot. So how we can get that is by remembering that big S equals little s times the mass, right? This was the definition of specific entropy. If I divide the mass over, you recognize that. Now, big S dot equals little s times m dot, okay? I'm gonna make the equation dotted. There's m dot, our mass flow rate now. So delta big S dot, or the change, is the change of each one of those things. See, I put the delta on either side. So this is what we can use to, and finally, I'll write out what delta M is. And this is m dot in minus m dot out. Okay? That's just simply the change in m dot, in minus out, how much it's changing by. So taking this and plugging it back into our equation, we have minus little s m dot in minus m dot out equals our unknown S gen. Last step is to plug in numbers. We have minus 5,000 times 1 minus 1.3. And when I calculate that, I get a total answer for entropy generated of 1,500 joules per Kelvin per second. So the answer for in 1 second, 1,500 joules per Kelvin. Okay? All right. One more board to go. All right, here we are. 500 grams of liquid water is heated, increasing the temperature from 25 degrees Celsius to 80 degrees Celsius. What is the increase in entropy of the water during this process? Use an average specific heat for water of 4,186 joules per kilogram Kelvin. So we notice that the water is liquid, which means it's incompressible. And we also notice that there's no phase change. We know that liquid water from 25 to 80 degrees is all liquid. We're not crossing into a mixed region. And so we're going to use the formula for the entropy change of an incompressible substance, the formula we have for solids and liquids, which is that delta S equals MC ln of T2 over T1. Okay? Recognize that formula, hopefully. T2 and T1, well, we could just plug in numbers right away. My only note is these will need to be converted, so make sure that you don't plug them in Celsius. Mass, make sure that you convert that 500 grams into 0.5 kilograms. C is given all in good units, 4186. And the natural log, we'll have to convert our temperatures, and once you do that, you get T2 of 353.15 and T1 of 298.15. As a little note, in case we need a refresher on this, T2 is the temperature at state 2, so it's the final temperature. T1 is the initial temperature, because it's going from 1 to 2. Okay, that's how I know which one is which. And this is just a calculated problem. Punch that in, and you get out an entropy change of 354.3 joules per Kelvin. So really, by giving you that formula, all the work is done. I mean, you just come to the exam prepared with that formula, and it's plug and chug from there. Okay, just plug in your numbers. The only thing with this question is make sure to do the proper conversion in temperature, and I suppose in mass as well. This one here is very similar, but it's going to require a little more work. Okay. The reason why, let's read it. 0.4 kilograms of superheated refrigerant 134A is heated at constant volume, increasing the temperature from minus 25 degrees Celsius to minus 10 degrees Celsius. What is the increase in entropy of the refrigerant 134A during this process? Use average specific heats of Cp equals 794 joules per kilogram Kelvin, and Cv equals 712.5 joules per kilogram Kelvin. So this is actually referring to a compressible substance, because you could check in the back of your book, but at these temperatures, refrigerant 134A is a gas. Okay, it's already boiled off, even at these low temperatures. That's one of the reasons it's good for a refrigerant. So what we're going to need to do is remember the formula for the increase of entropy of a compressible substance, or a gas, okay? So we have delta S equals, oh, and this is also at constant volume, okay? So this is the one that has Cp in it, like that. MCP ln of T2 over T1. So as I've pointed out before, that first term looks very similar to that first term. The only difference is now we have a second term, which is minus mR ln of P2 over P1. Now you'll notice that no pressures are given. So the pressures here are going to be computed using the ideal gas law. The reason that we know this is because this thing already is only valid for ideal gases. Okay? So, or it's derived using the ideal gas laws. I'll say that. So we're going to, remember, need to use P times V. I can do specific volume if I want. Equals RT. That's the ideal gas law. And we'll be able to get pressures from temperatures. So if I make ones on P1 and T1, remember V and R are not changing, so I don't need subscripts. I get that P1 equals T1, well, I'll write it like this. A ratio in front, R over V, times T1. And then for the second pressure, P2, that's R over V times T2. So I'll star these. We've got two equations right here. From this point, there's two ways to arrive at the same answer. It's really the same calculation, but it's just, are you going to take the slightly longer way or the shorter way? The longer way would be to plug in numbers right now and compute P1 and P2 and do the ratios and plug everything in, compute R by taking the difference, and compute this as two separate terms. I'm going to take what I'm calling the short way, and the sacrifice for that is doing a little more algebra. Okay, I want to manipulate this a little bit more. So what I realize is that if I take the ratio here, symbolically, I have, I should do 2 over 1, right? So I'm going to take this whole equation and divide by that whole equation. P2 over P1 equals T2 over T1. So what I'm going to do is erase this and just write T2 over T1, because that's what we get. Now notice that I've got a redundancy here. This log of T2 over T1, is showing up in both of those terms. So what I'm actually going to do is factor out the coefficients. Let's see what I mean here. Delta S equals M times Cp minus R times ln of T2 over T1. Okay, if you need to think about where that came from, that's fine. But this log term was in both. So there is your two terms. Okay? Now, the property that we remember, and either way you do this, you'll have to remember this equation. You'll have to remember that R equals Cp minus Cv. Okay? We'll remember that, and that'll help us go into there. So, I can write Cp minus R. If I move R to this side, and if I move Cv to this side, I get Cv equals Cp minus R. What that ends me up at is delta S equals mCv ln of T2 over T1. A much simpler formula to plug numbers into than up here, only at the cost of thinking through a little bit of algebra. So plugging in numbers, 0.4 kilograms, Cv is 712.5, and be sure to convert those temperatures. So T2 is 263.15, and T1 is 248.15. All right. When I solve that on my calculator, it comes out to about 16.72 joules per Kelvin. Okay, those are the most intense problems done. Here we have the last two questions. They're not too long. Water at 200 kilopascals has an entropy of 3,000 joules per kilogram Kelvin. What is its quality? Well, there's not a lot of information given. So if you're given this little information, you're going to know, okay, the only thing I can do is get information from the lookup tables in the back. Okay? So I'm going to go to the lookup table for water, and I need the pressure table, so don't accidentally end up at the temperature table. That won't be the exact pressures. Go to the pressure table for, now again, how do you know if it's superheated or saturated? Well, it asks about quality. Okay, if the water was superheating, meaning totally all gas / vapor, it doesn't have a quality. So the fact that we're told it has a quality, what is its quality, means that we're talking about water in the mixed state. So we're on the saturated water temperature table. That's found on page 978. Okay? And in the exam, it will be the same page if you want to memorize the page number. Okay, I'll just change the pressure. So if you recall the formula we had for quality before, we did it in terms of specific volumes. And here's what we had. It was VT, meaning specific volume total, the one we actually had, minus VF, the specific volume at which the saturated liquid line was, okay? F is for fluid, because it's the saturated liquid line. And then over VFG, which was the difference in VF and VG, the saturated liquid and saturated vapor lines. This number told us the width of the span, right? Is it a small span or a large span? Okay. Now notice that that's just a ratio and it's unitless. We've discussed the fact that quality is a unitless quantity. So I don't have to use specific volume as my property. This is just as legitimate as using specific entropy. And that's exactly what we're going to do, because that's what we're given. It's the same exact thing. I've just swapped it out with entropy. So when you go to your table on page 978, you'll just get the numbers from the entropy column. So go down to where pressure is 200 kilopascals in this case, and start filling in numbers. ST is what we're given, which is 3,000 joules per kilogram Kelvin, but in the table it's kilojoules per kilogram Kelvin, so it's just 3. SF is about 1.53. This is read straight out of the table. And SFG is 5.60. I encourage you, specifically on this one, to go to that page and make sure that you can come up with those same numbers. And I simply evaluate this and get out a quality of 0.2625. So about 26% vapor, the reservoir. Last question here. A reversible power cycle draws heat from an environment at 40 degrees Celsius and operates with an efficiency of 85%. The lost heat is ejected to a cold location. We know that from the second law, it must be. At what temperature? So first, 40 degrees Celsius, let's translate that as 315.15 degrees Kelvin, okay, just as a note. And we'll remember our efficiency formula. So this is a reversible power cycle. So we have a formula for that. It's 1 minus T low over T high. If you need to refresh your memory on that, you can do so. That's simply our efficiency formula for reversible processes written in terms of the temperatures. And then plugging in numbers, we know this side is 0.85. We know the T low, I'm sorry, that's T high that we know. T low is our unknown. T low is 315.15. Or T high, I'm sorry. Okay, temperature we know is T high. It's clear in the question, I'm just getting my brain addled. So we do this. I'm going to swap the 1 and the 0.85 with this. So I'll move this over and put the 0.85, ending up with T low over 315.15 equals 0.15. I've done the subtraction there. 1 minus 0.85. And then I'll multiply both sides by 315.15 to get T low by itself. And it comes out to be 46.97 Kelvin, which is absolutely incredibly frigid. I could have done a better job making up imaginary numbers, but it's the correct answer for the problem that I made up. Okay, so good luck on exam 3.